Okay, let's talk about problem 10 now, two-phase commit two furious. So the first part is a true or false, where we have four true or false questions. The first one is, presumed abort always results in fewer messages sent across the network than regular 2PC. This is true or false. So in the case that there is an abort, this can be true because then we would, with our presumed abort optimization, we would save in terms of the amount of messages being sent in the case that a node knows that it's going to abort. However, in the case that everyone votes yes, so we actually have a commit, the process isn't actually any different than a regular 2PC. So in that case, there wouldn't be any fewer messages sent across the network. It would be the exact same. So this is false, right? It's not that presumed abort always results in fewer messages. It's just that there are some cases where it does result in fewer messages, but not always. And then the same reasoning applies to part 2 as well. Okay, part 3, machine M1 can be the coordinator for transaction 1 at the same time that machine M2 is the coordinator for transaction T2. So the rule is, right, each node should only have one coordinator. And in this case, right, each transaction only does have one coordinator. So there's no issue here. It's just sort of separate processes going on at the same time, but that's completely okay as long as no transaction has multiple coordinators, because then that would get confusing. Then part 4, if all participants crash at the same time, the transaction will always abort. Let's say all the participants vote yes, and then they get a commit message sent back to them, and then let's say they crash after sending an acknowledgement or something like that. Well, then in that case, there would still be a commit, right? Because as long as they all voted yes, there's like guaranteed to be a commit, assuming the coordinator doesn't crash. So in this case, this is false. Right, the transaction isn't always going to abort in that case. Okay, now let's look at part B of this question, which is pretty involved. So our database runs 2PC without any optimizations, with coordinator C and 3 participants, P1, P2, P3. The communication latencies to send a message between each machine are shown in the diagram below. All latencies are in milliseconds. The latencies are symmetric, i.e. it takes 200 milliseconds to send a message from C to P1 and then vice versa from P1 to C. So yeah, so this is kind of the entire thing. Notice like we already pretty much know like it's not going to matter what the latencies are between the participants because they don't need to communicate with each other, right? It's just the coordinator corresponding with each individual participant. So really the key numbers here are going to be between the coordinator and participant 2, between the coordinator and participant 1, and between the coordinator and participant 3. So we're told to assume the following information. Flushing a log record to disk takes 50 milliseconds. All other operations occur instantaneously except for sending messages, obviously. Timeouts will occur after 2,500 milliseconds. All participants will vote yes. When a participant wants to ask the coordinator about the status of a transaction, it sends a status inquiry message. For the rest of this question, consider the following chronological sequence of events. All event times are shown in milliseconds since the 2PC round began. So, C begins the 2PC round at 0 milliseconds. Participant 3 crashes at 500 milliseconds. Participant 3 recovers at 1,000 milliseconds. The coordinator crashes at 1,500 milliseconds. The coordinator recovers at 2,000 milliseconds. So notice that like while these crashes and recoveries are happening, the 2PC round is also occurring simultaneously, right? Because that began at 0 milliseconds. So we're going to sort of fill this in here and like fill in the 2PC round and show what happens like with these crashes and recoveries. So I've already gone ahead and done that, and we're just going to go over it. So the leftmost column indicates time in milliseconds from the beginning of the 2PC round starting, and then each of the other columns shows like the actions of the coordinator, participant 1, participant 2, and participant 3 at that timestamp. So there won't necessarily be something happening for like all of them at that timestamp, but at least something will be happening at all of the timestamps that I've listed. So, okay, at the first timestamp 0, right, when the 2PC round begins, the coordinator sends out a prepare message. Then, because the latency between the coordinator and participant 1 is 200 milliseconds, participant 1 receives that prepare at 200 milliseconds. It flushes that prepare. Remember, that takes 50 milliseconds to do the flush. So it doesn't send the yes until 250 milliseconds. Then participant 2 receives the prepare at 300 milliseconds because there's a 300 millisecond latency between the coordinator and participant 2. It flushes the prepare, that takes 50 milliseconds, so then it will send the yes back to the coordinator at 350 milliseconds. The 400 millisecond latency between participant 3 and the coordinator means participant 3 receives the prepare at 400 milliseconds. It flushes the prepare, that takes 50 milliseconds, so it sends the yes back to the coordinator at 450 milliseconds. Meanwhile, also at 450 milliseconds, the coordinator receives the yes from participant 1, because remember participant 1 sent that at 250 milliseconds, the latency between them is 200 milliseconds, so the coordinator receives the yes at 450 milliseconds. Then at 500 milliseconds, participant 3 crashes. Remember we were told that in the problem prompt. Okay, then at 650 milliseconds, the coordinator receives participant 2's yes because participant 2 sent that yes at 350 milliseconds. The latency is 300 milliseconds. 350 plus 300 gives us 650. Then at 850, the coordinator receives participant 3's yes, and that is because participant 3 sent that yes at 450, and the latency is 400 milliseconds. So 450 plus 400, 850, it gets that yes from P3 at 850 milliseconds. And because it's gotten the coordinator's gotten a yes from P1, P2, and P3, which is all of the participants, it can then flush the commit at that time. That takes 50 milliseconds. So then at 900 milliseconds, right, 50 milliseconds later, it will send the commit to P1, P2, and P3. Meanwhile, at 1000 milliseconds, P3 will recover, right, because we're told in the prompt it recovers at 1000 milliseconds. It sees the prepare in its log. Remember, it logged that over here. So it knows to that like there's a 2PC round going on right now. So it sends a status inquiry to the coordinator. That's going to take 400 milliseconds to land, right? That's the latency between them. So, but meanwhile, before that happens, at 1100 milliseconds, the participant 1 receives the commit that the coordinator sent at 900 milliseconds. Remember, 200 millisecond latency, so it receives that at 1100 milliseconds. It receives the commit, flushes that. That takes 50 milliseconds. So at 1150 milliseconds, it sends an acknowledgement back to the coordinator. Then at 1200 milliseconds, participant 2 receives the commit. Remember, 300 millisecond delay. So the coordinator sent commit at 900. 900 plus 300 means that participant 2 is going to receive the commit at 1200. It flushes the commit. That takes 50 milliseconds, so it sends the acknowledgement back at 1250. Then participant 3 receives the commit at 1300. It flushes that commit and sends the acknowledgement back in 50 milliseconds later. So the acknowledgement gets sent at 1350. Meanwhile, that's 1350 is 200 seconds or 200 milliseconds later than when participant 1 sent its acknowledgement. So the coordinator will receive participant 3's acknowledgement at that time. At 1400, participant 3's status inquiry finally lands, the one that it sent at 1000 after recovering. So the coordinator receives its status inquiry and sends P3 a commit message. Say, yeah, we committed. This is what happened while you were gone. Notice how that's kind of redundant because P3 actually did end up receiving the commit over here. But P3 didn't know that it was a commit at the time of recovery. It only found that at 300 milliseconds later, which is why, yes, there's going to be some repetition here. So we need to watch out for that. But then at 1500 milliseconds, we're told by the prompt that the coordinator crashes. So there's a crash at 1500 milliseconds. Meanwhile, at 1800 milliseconds, participant 3 receives that like other commit. The commit that was sent here is received by P3 at this point. However, it already flushed that into the log, so it doesn't need to flush it again, but it's going to send back another acknowledgement so that the coordinator knows that P3 received the commit message. Right, because from P3's perspective, it might be like, okay, maybe the coordinator didn't get my acknowledgement. I'm just going to re-acknowledge this just so it knows that I know. Coordinator recovers at 2000 milliseconds based, again, on the prompt. So at this point, it doesn't see anything in its log. Like the first thing it sees, right, is this commit that it flushed here. So it knows that there's going to be a commit, but it didn't flush like the acknowledgements because it didn't receive the acknowledgements from P2 and P3 before it crashed. So it just resends the commits to P2, P3, and or P1, P2, and P3. So at 2200, P1, due to the latency, is going to receive that commit again. It already logged the commit, remember, so it's just going to send the acknowledgement again. Also at 2200, the interesting thing is the coordinator receives an acknowledgement from P3, and that's because P3 sent the acknowledgement at 1800 over here, and then that took 400 milliseconds to travel. So the coordinator gets the acknowledgement earlier than either P1 or P2. So it gets a P3 acknowledgement at 2200. Then at 2300, it's commit message to P2 lands. So P2 receives that commit, again, already in the log, right? We had already flushed that into the log over here. So it's already in the log. It sends back the acknowledgement. At 2400, the coordinator receives the acknowledgement from P1. At the same time, P3 receives the commit message from the coordinator. Again, that's already in the log because notice it flushed the commit message all the way up here. So the commit message is already in the log, so it's gonna send the acknowledgement again, just for the same reasoning as, okay, maybe the coordinator hasn't gotten my acknowledgement. I'm gonna make sure they know that I know that it's a commit. So participant 3 sends that acknowledgement, and then at 2600 milliseconds, the coordinator receives participant 2's acknowledgement, again after some latency. And at 2800 milliseconds, it receives the acknowledgement from P3. So yeah, if that was a little bit too quick, feel free to go back over, pause the video. Let me just quickly scroll through the schedule again. So I'll give you some time to pause the video and take a look at it. Okay, so now let's go over the questions. So there's an important note here which says a coordinator sending a message to all participants at the same time counts as sending one message. So like when it sends that prepare at the beginning to all the participants, that's not 3 messages, that's just 1 message. And then we're also told for questions that ask at what time an event occurs, provide the time in milliseconds since the 2PC round began and just the number. So we're asked, what is the first message C receives, the coordinator receives? So let's take a look. So let's just scroll down the coordinator's column and see, okay, the first thing it receives is a yes from P1 at timestamp 450. So the first thing is a vote yes from P1. And then we're asked, what is the latest time at which C receives vote yes? So the latest time, right, so it receives a vote yes at 450, it receives a vote yes at 650, and it receives a vote yes at 850. 850 is the last vote yes it gets, and that's the one from P3. This is going to be 850 milliseconds. For this question only, assume the answer to the previous question is 750. So assume that C received the vote yes at the last vote yes from P3 at 750 milliseconds. What is the earliest time at which C sends the commit? So if you'll recall, what happened when it was 850 milliseconds was that C realizes, okay, everyone voted yes. That means it's a commit. Now it flushes the commit, and that takes 50 milliseconds. So it takes 50 milliseconds from the time of C receiving the last yes before it will actually send the commit message to everyone. So even if we assume that it's 750, it's just going to be 50 milliseconds after that before C, the coordinator sends the commit message. So that's going to be 800 milliseconds. Okay, so then part 4, select all the following that belongs in the blank. At time blank, C receives acknowledgement. So our options are 1350, 1550, 2000, and 2400. So let's check all of them. So it does receive an acknowledgement at 1350. Then let's check 1550. Doesn't receive an acknowledgement at that point. Check 2000. It does not receive an acknowledgement at that point. Okay, check 2400. Yes, it receives an acknowledgement at that point as well. So it receives acknowledgements at times 1350 and 2400. Okay, then part V, or 5, select all the following that belong in the blank. At time blank, C sends commit. So let's see when C sends commits. Our options are 850. C doesn't send a commit at 850, it flushes a commit. Then the next option is 2000. The coordinator does send a commit here, right? It sends it to all of them because that's when it recovers, so it sends all the participants a commit. So it does send a commit at 2000. Next option is 2200. It does not send a commit then. Next option is 2400. It does not send a commit then. So the only time that it sends a commit of the options given is going to be at 2000 milliseconds. Then part 6. For this question only, assume that C sends 4 commit messages in total. How many messages does C send in total? So for this, we assume, okay, 4 commit messages. Ignore the commit messages it sent. We're assuming it's 4. And then we want to find out, okay, how many other messages besides commit messages did C send? So let's just go through everything. So we see here that C sent a prepare message at timestamp 0. Okay, that's one message it sent. And then it sends a commit at 900, but we're not counting the commits, so still just one. A commit at 1400, we're not counting the commits, so still just one. A commit at 2000, not counting commits, still just one. And so yeah, it looks like the only thing it sent was the prepare. So it's just going to be one prepare plus 4 commits, because they tell us to assume 4 commits, which means that C sends 5 messages total. Remember that as far as how many messages it sends, we're not counting like one thing as 3 messages, right? Like sending prepare to participants 1, 2, and 3 is just one message. So that prepare is just one, even though technically it did send 3 messages, that just counts as one message. And then we're told it sends 4 commit messages, so that's going to be 5 messages total. Then for part 7, select all of the following that belong in the blank. At these timestamps, P1 begins to flush a log record to disk. So the options are 100. So clearly it's not flushing anything at 100. 200, it does do a flush at 200. We can see here it flushes prepare. And then 1100. So yes, here it flushes a commit. And then 2200, no, it didn't actually do any flush there because the commit was already in the log. So it does the flushes at 200 and 1100 of the options given. Okay, then part 8, how many messages does P1 receive in total? So let's just go back and check that. Let's go through here. So at 200, it receives a prepare, that's 1. At, let's see, at 1100, it receives a commit, that's 2. At 2200, it receives a commit, that's 3. So total, it receives 3 messages. Receives 3 messages. Okay, for part 9, we're told, for this question only, assume the answer to the previous question is 6. How many messages does P1 send? So P1 received, in our example, 3 messages, so it sent back 3 messages, because it responds to every message. So if we were to assume it receives 6 messages, well, that means it sends 6 messages, because it sends 1 message for each message it receives, and that's because P1 never crashed, right? Only P3 and the coordinator crashed. So P1 never crashed, so it's always going to respond to every message. So if it receives 6 messages, it's responding 6 times. Okay, then part 10. Select all of the following that belong in the blank. At timestamp blank, P2 begins to flush commit to disk. So let's go through these. Our options are 300. So P2 is at timestamp 300 flushing prepare, not commit. So not that one. Other option is 500, not doing anything there. Next option is 1200. And we can see, yes, in fact, P2 is flushing a commit here. So 1200, and then 2300, no, the commit was already in the log, so it doesn't flush it again. So our only answer here is going to be the 1200. Okay, part 11, select whether the following statement is true or false. P2 sends more messages than P1. Okay, let's find out. How many messages does P1 send? P1, remember, sends 3 messages, so we could just go through that again. So P1 sends a yes at 250. It sends an ACK at 1150. So that's 2, and then it sends an ACK at 2200. So P1 sends 3 messages. Then let's see how many P2 sends. P2 sends a yes at 350. It sends a ACK at 1250, and then it sends another ACK at 2300. So they're actually equal, and so this would be false. P2 sends the same amount of messages as P1, not more. Then part 12, select all of the following that belong in the blank. At timestamp 5, or after timestamp 500, P3 sends which of these messages? So let's go to timestamp 500 and just scroll down. So we see P3 sends a status inquiry at 1000, so status inquiry, and it also sends an acknowledgement at 1350, and then it also sends an acknowledgement at 1800. So, and then it also sends an acknowledgement at 2400. So it sends a status inquiry and then 3 acknowledgements. So status inquiry, status inquiry, as well as acknowledgement. What machine sends the final message? Okay, let's take a look. So looks like it's P3 right here. This is the last message that's sent by one of the participants. So that's at 2400. Well, it just says any machine, so the coordinator is included, but also the last time the coordinator sends something is 2000. Last time P1 sends something is 2200. Last time P2 sends something is 2300, and the last time P3 sends something is 2400. So it's going to be P3 in this case is the last machine to send something. What is the earliest time at which an end log record can be emitted? So this is the time at which the coordinator has received acknowledgements from every participant. So notice that the coordinator receives an acknowledgement from P3 at 2200, it receives an acknowledgement from P1 at 2400, and it receives an acknowledgement from P2 at 2600. So by 2600, the coordinator has received acknowledgements from all the participants, so it can just emit an end record at that point. It doesn't need to wait until 2800 because it already received an acknowledgement from P3. So at that point, that's just redundant and it doesn't need to wait. So at 2600, the end record can be emitted. Okay, last question, 15. Consider an optimization to 2PC where the coordinator flushes an ACK log record every time it receives an ACK from a participant. In case the coordinator crashes, it will know upon recovery which participants have already sent an ACK. Using this optimization, how many milliseconds earlier can an end log record be emitted in comparison to the regular case without the optimization? For example, if this optimization allows for an end record to be emitted at 4000 and the answer to the previous question is 4500, your answer would be 500. So in this case, logging the ACKs doesn't actually do anything to improve the amount of time that we can send the end at, right? Because we're still going to receive the last ACK at 2600. So that's still going to be the first time that we can log an end. So it's actually going to give us no improvement, right? 0 milliseconds faster. One thing to note, though, would be that if it was actually logging the ACKs, it would have logged this ACK right here. So it wouldn't need to send P1 the commit message here. It could have only sent it to P2 and P3 because it knows that P1 already acknowledged. And with that, we wrap up question 10. So good luck on your final.